All right, these are our last two slides here. We're wrapping up this module. I'm really excited to say that because this has been quite a lengthy module. And I know it's been a lot of material. Basically just going to quickly compare and contrast passive and active filters. Of course, we saw passive filters. They contain only passive elements, resistors, capacitors, and inductors. The difference with active filters is they can contain transistors, which we haven't seen transistors exactly, but we know that inside of an op amp there are transistors. So active filters include not only passive components, but also active components. And so this opens up a whole new range of possibilities. With passive filters, we don't usually get any gain unless there's resonance, which I didn't talk about in this module. I just ran out of time. If you just use LC filters, you can get some pretty serious resonant peaking where instead of just getting a typical low pass response, you can get something that actually gives you a peak in gain at a particular frequency right around your cutoff. And the sharper that you make your Q factor, which we also didn't talk about that, you can get even higher gains. And before your roll off right at a particular frequency, that all happens from LC resonance. So if you're interested in that, definitely look that up in the book. But with active filters, we can get more precise control over the kinds of responses that we get. So again, instead of, like I said, instead of having a low pass filter that starts at 0 dB and then rolls off at some frequency, we can have control over that RF over RS or whatever ratio of resistors to push this entire curve basically up the graph, right? So that we get something like 60 dB or a factor of 1,000 gain before we get our roll off, in case we're interested in not only attenuating higher frequencies but also boosting lower frequencies, right? This would give me V out over V in is a factor of 1,000, right? And so that's also desirable in a lot of cases, is to be able to boost your signal. Another difference between passive and active filters is that passive filters tend to be able to operate at much higher frequencies because they contain only passive components, but because active components are included in active filters, typical active filter ranges are limited to lower frequencies, typically less than 1 megahertz. Okay, that's greater than 1 megahertz, less than 1 megahertz. Okay, so one final thing about passive versus active filters is that when it comes to cascading filters, so like I talked about previously, if I have a typical low pass RC filter like this with, I know that the response looks like this, and this is going to be minus 20 dB per decade. Theoretically, I should be able to cascade a second filter here. Wow, I clicked on a lot of things. Should be able to cascade a second filter here. That would also give me 20 dB per decade roll off. And if I have two of those, I should theoretically get 40 dB per decade roll off. However, that doesn't exactly work with passive filters because the passive filter itself depends on the two component values. If I have an impedance here of a value R, and I have an impedance here of a value C, or sorry, 1 over j omega C, then I do get this initial 20 dB per decade drop off. But if I now take my original filter and I analyze it with not only this capacitor here, but another resistor and another capacitor, now I have to factor this resistor and capacitor into the impedance of this capacitor, because from the perspective of this resistor, it doesn't know what's over here. If I just have my capacitor here, then it knows that the impedance is 1 over j omega C. But if I add these other components, it doesn't know that. It just sees this giant block of components and it just treats it as a single impedance, right? And so no longer do I just have the typical RC, I have something else. So cascading passive filters doesn't work super great. However, cascading active filters does work super great. And I don't even need to cascade active filters. I can cascade passive filters with the use of op amps. So if I take this circuit here and I pass it into a, let me just delete this wire here. I pass it into a unity gain op amp, something that looks like this. And then I go into another filter, just like this. I would have no issues with loading. Why? Because the input impedance of an op amp is zero, or is infinite, ideally infinite, right? So that means that from the perspective of the resistor, it sees my capacitor in parallel with an infinite impedance, which basically means it just still sees the capacitor. And so we have no issues with what I was talking about up here with the extra components basically loading my initial filter. I basically get the response I want from these. I have a unity gain filter, which basically replicates this voltage over here. So this doesn't really do anything to my voltage. It just passes it right on through, right? My unity gain follower, basically. Sometimes it's called a voltage follower. And then I could have another filter out here with another 20 dB per decade drop. And so my overall response would be something like this 40 dB per decade drop, and all made possible by this op amp. And because active filters use op amps, they also have very good properties when cascading them, right? So going back to my active filter example, if I just stacked two of these, one right after the next, I take this V out and feed it right into a new RS, right? And create another filter here with another op amp, just like that, I would get 40 dB per decade as well, because active filters are good for cascading. Passive filters are not good for cascading, okay? So that is it for this module. I've got no more slides, and I'm very, very happy. So I'm going to go ahead and end this video right here, and we will see you guys in module 3.